Swayam Prabha. Digital India. Educated India.
Our basic bracing case here. So there's in the analysis models folder on the Google Drive, there's a file that's basically a CSM file for Consteel that says tutorial session 4 nodal bracing problem. So let's pull that up and look at it together. So I'm going to use the model in Consteel to kind of explain the problem that we're solving. So this is a problem that is an example in the AISC Design Guide 28 on basically stability design of buildings. What you're looking at here is a model of a situation where you've got some sort of a vault or an opening that this column is adjacent to. And so the column is needing to span from top to bottom 18.288 meters or 60 feet, top to bottom. And there's no because of that's it could be a boiler that we're supporting in there, or it's some kind of a shaft that's an opening that we can't put framing into. So that column has to span that entire height from top to bottom, but we can brace it at the top and the bottom. Okay? Now, if we were just going to rely on column, designing that column for flexural buckling over that 60 feet, well, that's a relatively long length. So what we're going to try to do is to put in some a moment connected beam. A typical term for this is a flying beam that basically flies across and is framed into this column there at its mid-height. And so you can see how that's working there, right? So that's still a relatively lightweight beam there that's framed into the middle of the column. And then, in that beam, the total span of that beam is 30 feet across this shaft or opening. And so we can basically tie that beam in, simply supported, into other stuff at its end. Now, in addition, as we essentially we've got 4 stories here of that are each 15 feet, and so within the plane here adjacent to the shaft, we were able to get some rod bracing or something in to brace the length. So in the weak axis bending direction of our column, we've actually got an unbraced length of 4 unbraced lengths of 15 feet. All right. Again, it's simply supported at the top. That's it. That's pretty much our system. Now you can play with this. If we turn it to a line mode, you can click. Let me turn off the portions dialog there. So you can click on a bracing and say, okay, yeah, I'm supporting the column at the top. in the X and Y direction, and I'm preventing twist at the top of the column. So that's my boundary condition at the top of that column. So I'll hit delete selection to take away that. If I look at the boundary condition that we're using at the ends of the beam, X, Y, X, X, so we're preventing twist at about the X-axis at the end of the beam, and we're preventing X and Y displacement, but we're allowing Z. The reason for that is if I restrain the Z, I would get something where when the column shortens, I would get some weak axis bending in this flying beam. And so we're basically looking to try to do an idealization where we're not going to be producing bending in that beam, right? So here again, the beam is strong axis bending in terms of supporting the column, buckling major axis bending in the direction normal to this side of our shaft. And other detailed boundary conditions. If we zoom in, if I click on this guy, I can see, well, I got to delete the other one. Okay, so click on here. Oh, that's just a support in the X direction. So that's like just giving me rod bracing into the web there at the middle. So remember, we have a situation like this, we might need to worry about torsional bracing or torsional buckling, right? Again, we're spanning 60 feet, except we're grabbing the middle of this, and it's major axis bending in and out of, or normal to this wall of the shaft. Our flying beam is in major axis bending to try to provide support to the middle of the column. Okay, so let me ask you, what type of bracing is this? What type of bracing is the flying beam providing to the mid-height of the column? Nodal, Yarrow point, right? Okay, this is a good example of a nodal brace or a point brace. Okay. Let's see, what else? Now the sections here, if I select on the column, you know, when I define the column model here, I defined one member up for the whole 60 feet. Okay. Are you talking about the column? Yeah. Okay. And when you say you mean KZ?
KT, the torsional.
Okay.
I mean, it
KT
won't
is
matter.
J? What I call J is KT?
Yes, yes.
All right. Yeah. All right.
So KT will be equal to KY in this particular case. I mean, it's the usual case that the other day we were talking.
When we say KY there, so KT is basically sum of BT cubed over 3 of all the plate elements, right?
I was talking about the effective length in torsion.
Oh, okay. So
and effective length in the
we call
minor
that
axis.
KZ
Yeah.
then, right? Yeah, so let's talk about that. So with what I'm showing you here is KZ equal to KY. Again, these braces right here, what I just showed you when we clicked on that. Gotta delete that selection if I come here. So that's just support in the X direction only. I'm not.
Yeah, so KY, it'll be different. Yes,
Okay.
Yes. Okay. Thank you.
So if you basically said what's the unbraced length LY for the column, what would you say it is? The whole thing is 60 feet.
It's 15.
15, right? Yeah. Right, that's right. And then, but if you say, oh, well, what's the LZ?
It's 30.
30 feet,
Yeah,
right?
30 feet.
Everybody good? Okay. All right. So that's our situation here. So we'll come back to this view again. All right. So now I'm going to show you a few things that are fairly powerful in consteel. I guess the other thing I haven't shown you here, but there's a handout that's a PDF file that parallels this, that explains it, and that's what's the loading. And so we've got an axial compression coming in at the top of this column, 1,400 kilopounds, so 6,227.5 kilonewtons that we're supporting. And if I come back here to look at what is this column, if I click on it, I can see over here in the object properties table, that's a W14 by 145. I put that in imperial units. I should have put it in SI, but that's the nominally 14 inches deep, 145 pounds per foot for the column. Okay. And so this is exactly the load and the section that's in appendix, that's in Design Guide 28 of AISC. And then I'm trying to use here for the flying beam to get that brace at the top. Now we're getting bracing stiffness to the mid-height of that column by the bending stiffness of the flying beam, right? Okay, and you can see that's a W14 by 43. So we're going to look at trying to justify that W14 by 43. And we'll do that first, and we'll go to the handout once we've kind of worked this through Consteel a little bit. And then I'll show you at the end of that, we're kind of taking it in reverse order. We're looking at the more sophisticated or computational solution with Consteel first. Can we justify this W14 by 43? And we're going to justify it, otherwise why would I be showing it to you, right? But then if we were to use the Appendix 6 rules for nodal bracing, and we have and there's the rules are actually configured so that they're posed in a conservative way, but then you can go to the commentary and apply them in a more refined way, and so I'm going to apply it in that way. So even with all the refinements in the specification and commentary for nodal bracing, Appendix 6 would tell me I need a W14 by 61 rather than a W14 by 43 to brace this column. So with this W14 by 145 column with a load of 1,400 kips on it. So, and that's basically two sizes larger of a wide flange section. And we'll look at, well, okay, why was Appendix 6 conservative? It's basically because of the philosophy we take in Appendix 6. But then if we say, well, we're going to go more general than Appendix 6, we're going to apply a direct analysis to assess this problem. Okay, we can then justify a lighter brace. All right. Okay. So now a couple of things here. In Consteel, for this problem, if I do an analysis of this problem where I model a perfectly straight column and a perfectly straight flying beam, and I put axial force on it, am I going to get any force in the brace? It's just going to go straight down the column and it's going to stay straight, right? So that's the problem once we're trying to do stability bracing fundamentally. You know, the Appendix 6 equations avoid us having to set up an analysis and do all this fancy work. You can just say, oh, I just apply this formula and I get something. But I need a W14 by 61. Can I go lighter than that? Okay, you got to do some analysis. And the analysis has to consider imperfection, because it's the imperfection along with the axial load that's causing our brace force. Okay? we need an imperfection in that column. So in Consteel, if I select that column, I just want to select only that column here. Notice in this row right here, it says bow imperfection L over Z minus 1,000. So that's kind of a little bit of a cryptic notation there. But once you understand that, you basically say, oh, I can go there, I can put in minus 1,000, and it's going to put in an L over 1,000 bow in that column in the negative direction. So negative direction, I think, being here in the negative y. Okay, let's see. Yeah, negative y. Actually, no, I think it's going to be positive y. So I think it's a local thing going on there with that negative number. Notice the other thing is we had to, from the default, we had to rotate that column by 90 degrees in order to put it in major axis bending in the direction we've got it. Okay? All right, so now I'll be frank, I think that this is kind of a beta version of Consteel it's looking at how to implement the AISC provisions. And so a lot of different things that Consteel does, and so they have basically what we need to do for the direct analysis method calculations in here. To get at them, we have to go to a design parameters, and if we click on this here, these double dots, so I actually come in here to stability design settings, and I want to set basically a entity here for a design setting, and this particular entity under buckling or compression members, I want to run a direct analysis solution. So this is the way Consteel allows you to say, I want to put in a stiffness reduction. It's a little bit, I think if they were implementing it just for the American code and didn't have all the Eurocode stuff and everything else, or once they maybe improve this, it may be a little less obscure. But you can go in there and you can say, okay, I would like to take these stiffness reductions, and also I'll show you where we're going to calculate a tau factor for this column of 0.9052. I want to apply that tau reduction to the column as well. And you can they have it where you can choose to apply it. If you don't want to apply it to each of these rigidities here, you can just apply it to a selected rigidity. I'm going to go ahead and apply it to all of them. Now, note it says to apply this method, you have to define a notional load. Okay, so we'll go look at that, and we'll go to the notes in a minute and basically look at okay, how do we come up with the 0.9052 and for this extra tau b. Okay, everybody in a good place still in terms of how we're getting through this. Okay, so now. This is a little bit quirky, but basically Consteel assumes if you're doing direct analysis method, you want to do a notional load. So you have to turn on a notional load. It's just in this problem, I don't want a notional load. I want a bow imperfection on that column, and that's it. I want to run it with a reduced stiffness. Well, to include the notional load, I have to go to loads. And if we scroll through the menus here under loads, there's a global imperfections. And so Consteel actually would allow you here in general to even put in an out of plumbness, an explicit out of plumbness on a frame. Here. The problem is that if you want, the way Balint has this implemented at present, if you want to take a stiffness reduction of 0.8 or 0.8 tau, you have to have a notional load. And so what am I going to do here? I'm going to put in a notional load, but I'm going to set it to a really, really small number. So that's a little backhanded, but that way we can use the procedures that Consteel has with a reduced stiffness. So that's for the column. For the beam, I've got a different property object. If we go in here for design parameters, look at the, for the beam, I just want to do the 0.8 stiffness reduction. So I don't have the tau factor here. Okay? So we got a 0.8 stiffness reduction on all elastic stiffnesses here in this problem then. And in the column, because this is a relatively highly loaded column, very, very high load on the column, we're going to, by a direct analysis method, the specification revisions tell us to take an additional inelastic stiffness reduction factor on the column. Okay, so that's the setup of everything in Consteel. If we want to kind of inspect things going on, if I really zoom up, you can see, oh, that's actually the offset where I've got a bow in the column. Okay. All right. So now let's run our analysis. And so in the analysis, I have to tell it global imperfection notional load, and so all this will kick in, and I'm gonna do everything else similar to what we've done with the other examples. I'm gonna do a first order, second order, buckling analysis, and buckling sensitivity. And so if I do run, okay, let's run the calculation, and I'll go back to I'm gonna turn off this window and go back to drawing an image. And so, I mean, clearly, okay, that's the way it's deflecting. So I'm compressing this column, and the column is bending out of plane. It's apparent that I'm getting some help from that flying beam, but it's not really holding that point as if that point were braced, right? It's what we would call a partial bracing to that point. But hey, if I've got some stiffness and that's enough to where I can then make this problem work with a lighter brace, okay, so then good. I used 2 sizes smaller on this flying brace. Okay, if we look at some other information here with this, if we look at internal forces and bending moments, okay, so this is what the bending moments look like here on this. So you can see that restraint we're getting from the flying beam is definitely helping resist the bending of the column from this bow imperfection, at least some. And we can see what these are the major axis. This is the major axis bending moments that we're getting in that flying beam. Okay. So now let's go to the handout, and we can talk through what's going on with the problem. So this has a little bit of a textual description of what I explained to you, and basically showing you the image from Consteel of the problem. So I put in an out of plumbness of 30 feet over 500, but that would be 60 feet over 1,000. Probably should have said it as 60 feet over 1,000. So 18.288 millimeters is the out of alignment at the brace point in the middle that we would be required to consider to say, okay, now that's what I need to design my my bracing beam for. Now, if we're going to do a direct analysis of this, so here's my initial imperfection or out of alignment at the brace point. We usually, for out of alignment, you usually say L over 1,000, where L is the unbraced length between brace points, right? So it's the 60 feet over 1,000. we've got our 0.8 E, which is 160 kilonewtons per millimeter squared. We've got a PY, that's the area of our W14 by 145 column times the FY. We've got a PU that's 6227 kilonewtons. So PU over PY is 0.65. And so this is larger than 0.5. We're required by the direct analysis method to consider a reduction in the flexural rigidity. And so this is the tau B equation, and that reduction is 0.9052. So that's where the 0.9052 I just showed you in Consteel came from. If I were to, so Consteel is going to apply that to IX, and so this is the reduction on IX if I want to show it as just what the reduced value of IX is. Okay, so here's the screen capture of what I just showed you in Consteel for the way the system's deflecting. And here's the screen capture for the moments I was just showing you. So if we want to check what sort of brace force are we getting here, it's the maximum moment in that simply supported beam is PL over 4. So if we back solve for P, 65.38 kilonewtons. And so the ratio of the brace force to the force in the column is slightly larger than 1%. So that's actually not so bad. If we look at the nodal bracing or point bracing provisions, it's essentially the double of what we just did in the derivation with the panel bracing. So 0.01 is the requirement in Appendix 6. Oh, we're just barely larger than 0.01 here. And there's several reasons for that. One is that we haven't really exhausted the entire axial compressive strength of the column. So that's helping us some. Now, if we check the flying beam brace, so the MU there is okay. Actually, if we go back, I want to make sure it's clear here. I think I was just showing you moments here from first order. I need to show the second order moments. So these are the moments that we're working with. It's a second order analysis with a reduced stiffness. So these are the moments that we're actually working from. So now, if we look, okay, is that flying beam sufficient? I can consider the LP and LR of the flying beam, and the CB I've got here, which is 1.75, and I can determine that the CB, when we scale the uniform bending strength by CB, for the unbraced length we have of basically 15 feet in the flying beam, the ARSC beam flexural strength provisions tell me I can get plastic moment in that beam. It's got a compact section. So the VMP is 354 kilonewton meters of the flying beam. I'm actually only using 149.46. So our flying beam's got plenty of strength. We're good. If you try to use one size smaller and you go through all this, it fails, okay? So that would be a process you could use. If you're trying to lighten up that flying beam, you could use this type of analysis to get there. Now, to show you how would this work if we use the Appendix 6 rules. So I derived for you the relative bracing or panel bracing rules. The point bracing rules are a little bit more difficult to derive. But for this basic case with a single point brace at the middle, it works out when you do all the refinements. Oh, the point brace basically needs to have twice the stiffness and it takes twice the force. Okay? And so what you get with the commentary refinements in Appendix 6 is here's your required bracing stiffness, and so the 4 PR over and here it's an LQ. Again, the column does not have, is not loaded to its full capacity, and so the Appendix 6 requirements actually allow us to say, well, if I've given the 1400 kips on the column, let me back calculate how long of a column could I use that would have a capacity of 1400 for the W14 by 145. And so that would be 10.617. It's a little bit larger than 15 feet, 30 feet. And so that's what we can use there. It gives us a little bit of a benefit for the fact that we're not fully loading the column, but it's a conservative approximation. So if we take all that and put it in and calculate the value from the equation for the required bracing stiffness, it's 3.128. If we look at evaluating a W14 by 61, which is 360 by 91 in SI units. Okay, let's figure out, well, what bracing stiffness do we need? Well, a simply supported beam loaded at the mid-span, the mid-span load deflection, basically the stiffness is 48 AI over L cubed. And so let's substitute in there to find what this is the bracing stiffness we would be providing, beta actual, as a function of the moment of inertia of the beam. So let's set beta actual equal to the required bracing and solve for the moment of inertia we need for the beam. We need 249.1, and a W30 360 by 91 or 14 by 61 provides the moment of inertia that's slightly larger than this. So that's the size we would have to use based on the Appendix 6 rules. Then the beta actual on that is 3.34. We can plug that back into our required bracing strength equation. We get a little bit of reduction in the bracing strength demand because we're using an actual bracing stiffness larger than the required. And so this equation here then tells us, well, the bracing force we need to withstand is 58.6. The moment we're generating, the W14 by 61, is PL over 4. And that if we equate that to PMP, recognizing that for the unbraced length we have in the flying beam, we can develop plastic moment. So our PBR here is 58.6, but if we look at 4 times the phi factor times MP over L, solving that here for what do we compare to PBR, we can provide 227. So the W14 by 61 gives us more than enough strength to provide bracing to the column. So what the W14 by 61 is going to do is, if we go back to Consteel, if we ran it with a W14 by 61, if we look at the deflected shape, we wouldn't see a deflected shape like this. We would see a failure mode where it essentially is there's very little movement at the middle and the column buckles into an S shape. So here it's more of a partial brace, but it works. Appendix 6 doesn't give you the capability to do that, but you can go to direct analysis method to be able to lighten the bracing system and design the partial bracing fairly rigorously. Now, if we look at just a couple of other things here in Consteel, one thing that we would still need to do, but in the interest of time, we won't work through that. In general, we would need to check that the W14 by 145 column if it's bent into a mode that is an S shape, if it has an imperfection that's an S shape with an inflection point at the brace, that's the way that would be most damning in terms of imperfections on the column. If it is braced sufficiently, so you may have the largest moments in the column based on what we've got here and the moments in this problem. So these moments, second order here. But we would also need to check the column, is it still working if the imperfection is in S shape? And because, hey, is that brace enough to limit the moments in the column here at strength? So that's a little bit of a extra work that we have to do. We just justified that this brace is adequate in strength, but is it reducing the moments in the column enough to where the column still works? And the last thing, and let's take a break, and then I just want to do a really short segment, and we're going to wrap up early today. If we go to buckling analysis. So our buckling analysis here, let me turn this so that's, okay. Yeah, so it's actually buckling it toward us. We'll tone down the buckling mode there a little bit. Yeah, so the first buckling mode is kind of the way, what we're seeing here with the partial brace, right? We would expect to be getting some of the largest amplification of the displacements based on the way we put this bow in the column. But if we look at higher buckling modes, if I do 1.99, that's the buckling mode where the column is buckling into an S shape, huh? And if we go one more, let me scale that down a little bit. What kind of buckling mode is this? Torsional, huh? Okay, so if you were really alert, you might have been saying, wait a minute, I've got a rod brace into the middle of that. I better check torsional buckling over where KLZ is 30 feet, like we were talking about earlier. KLY is 15. So it turns out that that's not the critical buckling mode here in the problem. Okay, yeah, so yeah, I think you were looking at the equation I showed you for the nodal bracing. Good question. The question is are we doing 2 times or 4 times the ideal bracing stiffness here, right? Yeah, that's good. You noticed that. It turns out that the ideal bracing stiffness for the nodal brace here is 2 times PR over L, and the simplest way to conceptualize that is the derivation we did earlier for the panel brace. That's just one side. So now we got a top and a bottom, and both are pushing on the brace, so 2 times. Make sense? Okay. So the ideal bracing stiffness here for the point brace or nodal brace was 2 PR over L, and then we multiplied that by 2, and also we put in the phi factor on it as well.
Considering the area of or the size of the brace required, so what will govern more, the strength of the brace or its stiffness?
It's really problem dependent, right? And so we have both of those requirements that we always have to satisfy. So in this problem, I think, let's see, when we followed the Appendix 6 rules, it was the stiffness requirement that was basically requiring us to use that big of a beam, right? And let's see, when we were doing it by direct analysis method to justify the lighter brace, here also, when we check the strength, we're plenty good, and but then the stiffness is basically coming in by what we did everything here. You know, you could say, well, how do I know to try a W14 by 43? here for this beam? That would be a good question. The simplest way to do that is you could say, okay, well, I checked it by the Appendix 6. I needed a W14 by 61. Okay, great. I can model that. I can see I'll see that it's working. It's holding that middle of the column. I'm not getting any significant displacements there. But then I can say, well, okay, but that's an awfully big flying beam. I'd like to use something smaller. And so let me try one size smaller. And I say, oh, it works. And I'll find it works with plenty to spare. Let me try the W14 by 43. Oh, it's working. But I have to do all this analysis to do that. And I skip the part of, I also have to check the column to ensure that the column can still work, given I've got a much softer brace, right? If I go one size smaller, then it's not going to work. Okay?